Alright, this is section 4.4, and in 4.4 we talk about a specific way to find the limit of certain functions that up till now are not possible to do. These are of the form 0 over 0 or infinity over infinity, and when we look at certain functions we can't use our typical way of solving them because we run into problems of dividing by 0 and things like that. So if you have something of the form 0 over 0 or infinity over infinity, you can invoke L'Hopital's rule, which says at that point you can take the derivative of the top and derivative of the bottom, and this new limit, whatever its limit is the same as the original limit. And you can use it multiple times as long as you have 0 over 0 or infinity over infinity, so you might even have to use it 3 or 4 times for some problems. Now you want to keep in mind when you're taking the derivative of the top and derivative of the bottom, this is not invoking the quotient rule. Remember, the quotient rule is the bottom times derivative of the top minus top derivative of the bottom over the bottom squared. That is not what this is. This is just the derivative of the top, derivative of the bottom. Alright? This can be used for one-sided limits and for limits of infinity as well. So here we got a problem where we got 0 over 0. So we can use L'Hopital's rule. We take the derivative of ln of x, we get 1 over x, derivative of x minus 1, and we get 1. And that reduces down to just 1 over x, and now you can do direct substitution and you get an answer. Here you've got infinity over infinity. So we take the derivative of the top and we get e to the x, take the derivative of the bottom and you get 2x. Now we still have infinity over infinity. So we're going to take the derivative again, derivative of e to the x is e to the x, derivative of 2x is 2. Now when you plug in infinity in here, you get infinity. There's no longer division by 0 or infinity over infinity. Okay, and then this one, since you have infinity over infinity, you can take the derivative of the top, derivative of the bottom, and when you simplify each part, you get this. Now if you multiply by 2x, you're going to cancel all of the denominators, and it will reduce down to this. 2x times 1 over x is just 2. And 2x over 2 square root of x, your 2's cancel, and x over square root of x is just square root of x. And now when you plug in infinity there, you get 2 over infinity, which is 0. Same thing here. Alright, you've got 0 over 0, so you take the derivative, and you still have 0 over 0, so you take another derivative, top and bottom. Now the 2 over 6 can come out front, and it's really 1/3. The limit of, as x goes to 0, of secant squared is 1. So when we break this up into two separate limits, we know this limit is 1, we know this is 1/3. So we just have 1/3 here, but this guy here is still 0 over 0, and we use L'Hopital's rule again, and we take the derivative now, we can do direct substitution, and we get 1/3. Alright, this one, it looks like you might use L'Hopital's rule because you might think you have 0 over 0, but you don't. You have 0 on the top, but when you plug pi in for cosine, you get negative 1. 1 minus the negative 1 is really 1 plus 1, or 2. So you don't have to use L'Hopital's rule. You can do direct substitution and you get an answer. There's a number of problems from chapter 2 where if you use different techniques, you don't have to use L'Hopital's rule. Like here you can factor and cancel. Here you can expand and cancel with the h below, and when you go, as h goes to 0, you get your answer nicely. And here you can divide by the highest power of the denominator, and when everything else goes to 0, and you just get 3 over 5. So don't always use L'Hopital's rule every single time. There's a lot of times when you don't need to use it. Now there's questions of the form 0 times infinity or 0 times negative infinity. You don't really know what's happening with those, so you got to do a rewrite. Well, if you take one of the functions and write it as 1 over g instead of g, if it's f times 1 over g, if you flip this and multiply it times the top, you get f times g. So you can see that this does equal that. And you can also do the same thing with f. So you could flip either 1 and put it in the denominator. And that's what we're going to do here. We're going to flip the x and write it as 1 over x. Now we've got infinity over infinity, and we can take the derivative, and when we simplify it down, we just get negative x, and we can plug in direct substitution there. Now notice we flipped the x. You could have flipped the ln of x, but when you go to take the derivative, it's going to be a lot more complicated. generally you want to flip something that's simpler, like x or polynomials. Anything that's ln of x, you probably don't want to flip. It's going to be more complicated. Now you're going to have some that are of the form infinity minus infinity, or something of that nature. When you work with those, you can do one of three things. You can write them as one big fraction, get a common denominator. You can rationalize your numerator sometimes, or you can factor out a common term. And when you do that, sometimes you get of the form 0 over infinity, and and then you can use L'Hopital's rule. So like this one is two fractions. Each one goes to infinity. But when you find each one with a common denominator and bring them together, now you've got 0 over 0. You take the derivative and simplify it, and you multiply by a common denominator of x, and it cleans it up a bit. And now you still have 0 over 0. So then you take the derivative, and you get this guy here. It simplifies down to this. And now you can do direct substitution. Now this one is, you don't really know what's going on here, but there's an interesting way you can work this. You can factor out an x. Factoring an x out of the second one just gives you a 1, minus 1. But factoring an x out of e to the x gives you e to the x over x, which is kind of weird. But it's an interesting way to solve this. If you multiply x times this, you just get e to the x. Multiply x times minus 1, you get minus x. So this does equal that. So let's look at e to the x over x as x goes to infinity. Well, we can use L'Hopital's rule. And when we do, we find that that equals infinity. So this part here, the limit is going to go to infinity. Now when you look at that same term but subtract 1, it's still going to go to infinity. The minus 1 is not going to affect your limit. And we know that the limit as x goes to infinity of x is infinity. So now we've got infinity here, and we've got infinity there, and infinity times infinity will give you infinity. So if you break it down into smaller pieces and look at each smaller piece, you can sometimes figure out what's happening there. Now here's a weird one. Here's one where if you've got problems of the form f raised to the g, where both f and g are functions of x, you can rewrite it. And here's what you do. You start out with letting y equal the function f raised to the g, and then you take the natural log of both sides. And when you take the natural log of y, you get ln of y. When you take the natural log of f to the g of x, you can bring the g of x out front. And so you get g of x times ln of f. So now you want to take the, just watch what we do here. You're going to take the limit of ln of y, which is the limit of g ln of f. And when you simplify this down using L'Hopital's rule and other techniques, it will go to a specific number, some constant c. It always will. All right. So now, when you go back to the original question, f raised to the g, well, that's the limit of y, because we let y equal f to the g. And now, just like because if you say 5 equals e to the ln of 5, right? We're used to, with logarithm rules, we're used to being given this and simplifying it down to 5. But what if you go in the other direction? You take something and you write e raised to the ln of that number. Well, y equals e to the ln of y. Now, why would you want to do that? Because we know what the limit of ln of y is. We know the limit of ln of y is c. So this guy just becomes c, and that's what your limit goes to, is e raised to the c power. These will always, when you take this portion of the problem, will always equal a number, and when you work down here, it'll always simplify down to e raised to that exponent. All right. Now there's 26 problems in section 4.4, and I did all the problems that were similar to WebAssign numbers. So these are these line up exactly with the WebAssign problems. So I'm going to go through them very quickly, and you can just pause as you see each one on your screen. Alright, I can also do these. These are the problems out of the book. Okay, so you've got questions 9 through 15 there, and questions 17 to 21 there, 23 and 25, and 27 and 31, 33 and 35 and 37, 39 and 41, 43, 45 and 47, 49, 51 and 53, 55, 59, 63, 65, and 67, and 69, and the rest of 69. So the first set of questions I did, questions 1 through 28, those will line up exactly with your WebAssign questions. Those are the ones you want to refer to when you're doing the your WebAssign homework. But the extra exercises that I did there, those are out of the textbook that are similar to the WebAssign questions.